Hello, my name is Kathleen Smith, and I am a senior associate with the consulting firm Hazen and Sawyer. I am here today to present the findings of a regional water study as related specifically to Perry County. The regional study evaluated the adequacy of the water resources and associated infrastructure across Central Ohio throughout a 25-year planning horizon. The project was conducted by the Ohio Environmental Protection Agency, the Ohio Department of Natural Resources, in partnership with the Ohio Water Development Authority. The detailed modeling and analysis were conducted by the hired consulting firm Hazen and Sawyer. While the overall project considered water resources and infrastructure throughout a 15-county study area, this presentation will focus exclusively on the analysis and findings related to Perry County and its projected growth. The agenda for this presentation includes an introduction to the study and its objectives, a discussion of both the current and future conditions that were evaluated as part of this project, a presentation of the needs analysis of current and future water supply, demand, and treatment capabilities. The resource gaps and potential project options section identifies areas where existing developed water supply and infrastructure capabilities are insufficient relative to future needs. Insufficiencies are referred to as gaps. For each gap, potential project options will be presented. Opportunity areas have also been identified. These are areas where existing water supply or infrastructure capabilities will exceed future demands. In other words, areas where there is a surplus of water. And finally, water quality. We will close with a discussion of the projected changes to water quality throughout the planning horizon. Projected water quality impacts were developed based on projected changes to residential development, industrial development, and temperature and precipitation conditions. So let's begin with a high-level introduction to the study. The Central Ohio Regional Water Study was completed for a 15-county area, as shown on the map. The overall goal was to quantify current and future water-related needs within the region and identify areas with water-related gaps and surpluses. The study evaluated water-related needs that span drinking water supply, drinking water treatment capacity, wastewater treatment capacity, receiving water capacity, and water quality for the years 2030, 2040, and 2050. Project objectives were identified for the Central Ohio Regional Water Study. The objectives include improve, maintain, and optimize resources while planning for growth. Results of the model were used to evaluate opportunities to secure safe and reliable water supply for public use, consider reuse water for non-potable needs, and identify areas of capacity limitations. Future solutions were required to maintain beneficial use of water required for recreation, wildlife, and economic growth. Collaboration and regionalization. The project created a dashboard planning tool that will serve as a focal point for collaboration between utilities and state agencies, helping to ensure best use of both water and financial resources. Maximize funding impacts through sustainable infrastructure improvements. Using the analytic capabilities in the dashboard, state agencies can now and will in the future be able to help identify funding to build the infrastructure needed to meet the long-term needs for the region and identify future needs. The project also provides information to the state agencies on how stormwater and surface waters will be impacted by growth and development. The project can be used to identify opportunities to help mitigate impacts of development on the environment. Presentation will now shift to a discussion of the current water resources conditions in Perry County. This section will also include an introduction to the modeling that was completed for the evaluation of the overall water resources throughout the project area. Was developed to evaluate the available water supply, water demands, wastewater demands, and other uses of water throughout the region. The integrated model uses several components that are all connected to one another, as outlined in this graphic. Surface water, along with reservoirs and groundwater supply, feed either directly to water demands or feed a water treatment plant. That water treatment plant, in turn, supplies water demands, including the local population, golf courses, industries, and a myriad of other users. These water demands then go to a wastewater treatment plant, where the water is treated and returned to surface water or groundwater supplies. The water resources model developed for this project attempts to track all of the water uses in Central Ohio and determine if sufficient water supplies exist. The model evaluates if there is enough treatment capacity, if all demands can be met, and if wastewater treatment plants can treat the projected flows. The model was evaluated for the entire 15-county region. This presentation will focus on the current and future supply and demand for water resources in Perry County. Groundwater availability was estimated at the HUC 10 watershed level. To explain, HUC stands for Hydrologic Unit Code, and the 10 stands for the number of digits. The U.S. Geological Survey has delineated each of the watersheds in the country and assigned them a specific number based on their location, similar to a zip code. The system identifies drainage areas into regions, which are two digits, subregions, 4 digits, basins, 6, subbasins, 8 digits, watersheds, 10 digits, and subwatersheds, 12 digits. The map reflects the HUC 10 watershed level, and the watersheds in Perry County are labeled and shown on the map. There are 5 HUC 10 watersheds shown on the map. For each of the watersheds, the average daily sustainable groundwater available was estimated. These values are shown in MGD, or million gallons per day. It is important to note that the groundwater isn't uniformly available across the entire watershed. The color shading on the map indicates the recharge capability, with darker shading reflecting areas with high recharge, where groundwater would be more plentiful. One daily groundwater availability value was assumed per HUC 10 watershed, and all groundwater users within that HUC 10 were assumed to share that amount of groundwater. Groundwater supplies in Perry County range from 0.5 to 1.5 million gallons per day for a given HUC 10. Across these watersheds, an estimated total of 4 million gallons per day can sustainably be withdrawn from Perry County groundwater sources. There are a few disclaimers about the groundwater approach that should be noted. Scale. This study estimates total groundwater availability in each HUC 10 watershed as a single value, which makes its predictive capability only suitable for very large-scale assessments. The results are not suitable for site-specific analysis or any groundwater investigations besides those at a regional or sub-regional scales. Delineation. Aquifer boundaries do not always coincide with overlying surface water systems. In this study, groundwater boundaries are defined by surface watersheds, and consequently, some aquifers may be split by unsuitable borders. This may lead to unexpected or misleading results, especially near watershed boundaries. Uncertainty. Groundwater maps and studies always involve a high degree of uncertainty due to the complex nature of aquifers and the lack of widespread, reliable data sets of aquifer characteristics and water level information. While this is not unique to this study, its scale and time frame make its groundwater availability estimates especially uncertain. Site-specific groundwater investigations could mitigate these uncertainties. Egan and Associates assisted with the groundwater analysis and provided information regarding groundwater resources and conditions throughout the study area. For the Jonathan Creek Huck 10, sandstone wells with yields of 25 to 100 gallons per minute, or GPM, are possible in the central and northern parts of the Huck. Other parts of the Huck have little potential for high-capacity groundwater supply development. For the Center Branch Rush Creek Huck 10, an area of sand and gravel outwash aquifer of limited extent is present in the western part of the Huck, near the village of Bremen. Low-capacity bedrock in the rest of the Huck has little potential for high-capacity groundwater supply and development. For the Moxahala Creek Huck 10, low-capacity bedrock in the Huck has little potential for high-capacity groundwater supply development. For the Monday Creek Huck 10, low-capacity bedrock in the Huck has little potential for high-capacity groundwater supply development. For the Sunday Creek Huck 10, low-capacity bedrock in the Huck has little potential for high-capacity groundwater supply development. A limited extent of sand and gravel outwash aquifer may be present near the confluence of Sunday Creek and the Hocking River in the far southern part of the Huck. This study assumes that groundwater availability per Huck 10 is unaffected by land use and changes in precipitation and temperature, meaning that high recharge areas are assumed to be protected, and long-term cumulative precipitation is assumed to remain constant. This is contrary to surface water availability estimates, which are sensitive to both land use and climatic conditions. Is the cumulative sum of surface water from all watersheds in the county. However, surface water availability will vary for each stream location. Perry County is estimated to have approximately 6.5 million gallons per day of surface water availability. It should be noted that the surface water availability estimates are shown on this slide are raw runoff estimates and do not include modeled wastewater flows that are added to the streams. The surface water supply value is the minimum monthly average value for the current condition. Additionally, a portion of the surface water flows in Perry County are tributaries to the Muskingum watershed and are not modeled as part of this study. Adding both the groundwater and surface water supplies together, it is estimated that Perry County has roughly 10.5 million gallons per day of total available raw water supply. This supply availability is nearly split between groundwater and surface water, with slightly more available surface water. Supply availability at the sub-county level varies by location based on aquifer yields and surface water tributary area, as presented on the previous slides. The next focus for this resource evaluation was the existing and future demands that draw raw source water from the available water resources. Data on water demand was developed using population data, which was available on a regional basis. The information on current county population was obtained from MORPC, the Mid-Ohio Regional Planning Commission. These population data were used to further calculate water demand. The map on the slide is a heat map indicating the current estimated population distribution within the county. This estimate is for the year 2021, which is the year that the current conditions are based upon. Areas in blue tones are more densely populated, while the yellow tones indicate a less densely populated area. This map shows the assumed utility service areas for the county. Water demands were calculated for each utility using surface area boundaries. The population within the service area and recent historical water production data as reported to the Ohio Environmental Protection Agency. A per capita use was calculated for each service area. This was calculated by taking the water production data and dividing by the assumed population within a service area, which resulted in a per capita water use of gallons per person per day. This per capita water use includes all types of users within the service area, whether it is residential, commercial, or industrial. It is important to note that in future conditions, no service area expansion was assumed, and the water per capita use for each utility was assumed to stay the same. This means that growth in projected population would also mean a proportional growth in commercial and industrial demand within the utility service area boundary. For future water demands, the per capita water use was multiplied by the assumed future population within a service area. The total calculated demands for the county are shown in this pie chart, categorized by type. In total, the water demands are 3.8 million gallons per day in the county for the 2021 current condition. The largest portion of the demand is shown in dark blue, which is labeled as municipal demand. This demand is approximately 2.2 million gallons per day, and this is based on the population and utility boundaries discussed earlier. It should be noted that each demand can be served by either a public or private utility. The next largest demand, shown in light blue, comes from private water systems. Private system demand is calculated using the population not within an assumed service area. This population is assumed to be self-serving using groundwater wells. The per capita usage assumed for these private water users is 70 gallons per person per day. The total demand estimated from private water systems users is 1.6 million gallons per day. The municipal portion also has an associated wastewater component. The wastewater flow component in the county includes the used water from the service areas in addition to an inflow and infiltration component, or I&I, which was estimated and included in the wastewater flow. For the current condition, the maximum annual average wastewater flows are approximately 1.55 million gallons per day at the county level. The annual average wastewater flows were analyzed rather than the maximum month flows, as was done for water. This is due to the wet weather impacts observed in wastewater due to the infiltration and inflow impact. During rain conditions, areas with combined sewer systems could see very high flow rates, while during dry times only the base flow is observed. High rainfall in a single month could skew the average. Therefore, an overall annual calculation is used to determine if a particular plant is nearing its permitted treatment capacity limit. The existing demands and flows can be compared to the existing infrastructure. In Perry County, there are a number of water treatment facilities, and their total capacity is 6.4 million gallons per day. Most of that source water is pulled from groundwater, and some is pulled from surface water, or the local streams and rivers. Remember that the total maximum daily water demands are about 3.8 million gallons per day. So, in the current conditions, the county has sufficient capacity to provide treated water to meet demands. From a wastewater treatment plant capacity standpoint, the county has 2.6 million gallons per day of permitted capacity at the existing facilities across the county. The current max annual average wastewater flows generated by the demand and I&I are about 1.6 million gallons per day. And again, the existing county infrastructure is sufficient to meet the current wastewater flows. With an understanding of the current conditions in the county, the next step was to expand the analysis and explore potential future conditions. This study evaluated conditions in 2030, 2040, and 2050. When analyzing future conditions, current data is projected from the present to the future in time. With that projection comes uncertainty, which is why analyzing multiple potential future scenarios can provide more resiliency and reduce the risk of failure. Scenario planning acknowledges there are several plausible future conditions that may occur and allows planning for several possible future conditions. On the left side of the cone, there is only one point because current conditions are known. As time goes on, the cone of uncertainty expands and the range of possible future conditions widens. The widening could indicate divergence among the scenarios and changes in the recommended project that aligns with that scenario. Analyzing several scenarios or plausible futures helps ready the region for ending up in future A, B, or C, and knowing the projects to implement all along the way. 4 model scenarios were developed to define the range of potential futures. Scenario conditions that were explored were 2 different precipitation and temperature changes and 2 different population estimates, totaling 4 different model scenarios. The different inputs of these scenarios will be explored further on the following slides. 2 population sources were used for the scenario modeling. The expected growth trend was informed by the Mid-Ohio Regional Planning Commission, or MORPC. The MORPC population projections were informed by local zoning and land use plans. The historical growth trend was informed by the Ohio Department of Development, ODOD. The ODOD population projections are informed by historical birth, death, and migration trends. The population projections were used to estimate the future increases in municipal water demands and private water system demands over time. The bar chart on the left shows the different county level growth rates between 2020 and 2050 for the 2 population sources. The table to the right shows the future estimated total Perry County population for each source. The MORPC estimate results in a slight population increase, but the Ohio Department of Development estimate results in a population decrease. Municipal and private water system populations are assumed to change over time based upon the 2 population estimates that were just described. The left graph shows the municipal population over time for both population estimates, and the right graph shows the private water system population over time for both population estimates. The municipal population are the people assumed to be served by a utility. The private water system population are the people assumed to be outside of a water service area and having to self-serve groundwater from groundwater wells. The private water system population makes up a much greater portion of the population for the county, meaning most people in the county are not assumed to have water served by a utility. The expected growth trend estimates assume a population increase over time for both municipal and private water system populations, and the historical growth trend assumed a population decrease. The 2 heat maps show the current and future estimated population distribution within the county for the expected growth trend. The left figure shows the current or 2021 condition, and the right graph shows the future or 2050 condition. Comparing the two figures, there is minimal estimated population growth within the various parts of the county. Current and future land use data was also provided by the Mid-Ohio Regional Planning Commission, or MORPC. The left image shows the current or 2021 land use condition, and the right image shows the future or 2050 land use condition. The land use categories match that of the National Land Cover Database. For the current condition, a large portion of the county is pasture or hay land use, with various areas of development. Over time, very minimal land use changes are estimated within the county. Another element of the scenario modeling are the different temperature and precipitation scenarios projected. Historical precipitation and temperature data from 1983 through 2022 were used to estimate the surface water runoff and evaporation. For the future conditions, change factors were applied to the historical precipitation and temperature data to analyze the effects it may have on surface water availability. Temperature and precipitation changes were based on the global climate model data downscaled to the Central Ohio area. There are different change factors for each month and future planning year, 2030, 2040, and 2050. Change factors were extracted from an ensemble of 49 global climate models from the Intergovernmental Panel on Climate Change. 2 climatic conditions scenarios were selected for evaluation of future conditions: a moderate climate scenario and a hot and dry scenario. The moderate change scenario represents the middle of the road and utilizes the 50th percentile change factor for both temperature and precipitation from the ensemble of global climate model data. The top left graph shows the 50th percentile change factors for precipitation, and the bottom left graph shows the 50th percentile change factors for temperature. As the graph indicates, there is a greater change projected for temperature over the planning horizon. The extreme change scenario that was modeled is the hot and dry scenario, which utilizes the 5th percentile change factor for precipitation and the 95th percentile change factor for temperature. The top right graph shows the 5th percentile change factors for precipitation, and the bottom right graph shows the 95th percentile change factors for temperature. A scenario with no future temperature and precipitation change factors was also evaluated. The 2 temperature and precipitation conditions affect the future raw water supply availability, as the 2 different population estimates affect the future water demands. 4 model scenarios, all with different supply and demand conditions, were developed to reflect potential future conditions, as shown in the graphic. The intense pressure scenario consists of the 5th and 95th percentile temperature and precipitation change factors and the expected growth population estimates. The full speed ahead scenario consists of the 50th percentile temperature and precipitation change factors and expected growth population estimates. The easy does it scenario consists of the 5th and 95th percentile temperature and precipitation change factors and the historical growth population estimates. And lastly, the resource abundance scenario consists of the 50th percentile temperature and precipitation change factors and the historical growth population estimates. These 4 scenarios allow for planning of what different supply and demand conditions may look like and how those conditions compare to the infrastructure needed. As discussed, the different temperature and precipitation scenarios will impact water supply availability. In the model, the surface water supply availability was changed based on the temperature and precipitation change factors. However, groundwater availability values were unchanged based on these change factors. The graph shows total supply availability before any demands for both surface water and groundwater over time, for both change scenarios. Generally, the extreme change scenario, hotter and drier, results in less available surface water supply over time, and therefore less available total raw water supply. This bar chart shows the assumed future water demands over time in Perry County, broken up by type. As shown previously, current demands are mostly municipal demands, followed by private water system demands. With the expected growth trend, there are minor increases in both municipal and private water system demands. No future new or increased water or wastewater treatment capacities were assumed for Perry County. In this section, we will discuss water resource and related infrastructure needs at the county level. Combined surface water and groundwater supplies in orange. It shows max month municipal water demands in light blue and water treatment capacity in dark blue, all over time. Since the demands are less than the water treatment capacity and less than the raw water supplies for all years in the planning period, the treatment capacity and raw water supplies are sufficient to meet municipal demands at the county level. In this graph, the demands represented by the light blue line now include municipal plus private water system demands. The raw water supplies and water treatment capacity are sufficient to meet the municipal and private water system demands over time at the county level. Now, the non-municipal demands have been added in the solid and dashed light blue lines. The demands shown in the light blue line include municipal, private water system, and all non-municipal demands. Raw water supplies and water treatment capacity are sufficient to meet these demands at the county level. This slide presents similar information but relative to wastewater treatment capacity. On this graph, the annual average municipal wastewater flow for the expected growth trend is shown in light blue, and the wastewater treatment flow is shown in the dark blue at the county level. Existing wastewater treatment capacity is sufficient to meet future municipal flows at the county level. The previous section evaluated supply and infrastructure availability relative to demands at the county level. This following section will address resource gaps and abundances when you consider where those supplies, infrastructure, and demands are projected to occur within the county. The dashboard planning tool that was created as part of this study helps users visualize the resource gaps and resource abundances. The nodes on the map are color-coded by type and are sized based on how large of a gap or abundance there is for that given node. If a node is filled in red, that indicates a gap. Gap definitions are as follows. For a surface water node, is any shortage observed? For a reservoir node, does the usable storage ever reach 20%? For a groundwater node, does the remaining groundwater amount ever reach 0? For a water treatment plant, is the maximum monthly average flow greater than 80% of the permitted capacity? For a wastewater treatment plant, is the maximum annual average flow greater than 100% of the permitted capacity? This table summarizes resource gaps within the county for each scenario and model year. There are at most 4 gaps for any given year and scenario for the entire county. There are both infrastructure and raw water supply gaps identified. These gaps will be explored further on subsequent slides. Findings in the subsequent slides reflect the expected growth and moderate temperature and precipitation change in 2040. The 2040 full speed ahead scenario was selected as the target planning scenario to allow stakeholders to assess the current and future project needs without extending too far into the future, while using reasonable temperature and precipitation projections. The following slides will provide detailed discussion of the potential projects that could fill identified water resource and infrastructure gaps within Perry County. The project focused on identification of opportunities and strategies to fill those resource or infrastructure gaps. Gaps can be filled through a variety of ways depending on the type of gap. For example, a supply gap could be filled by constructing a reservoir or implementing a policy to restrict use during times of low supply availability. Other solutions include expanding treatment capacity and leveraging reuse water. Gaps are often filled with a project or a set of projects. A gap or set of gaps can be filled a variety of ways and can exist across some or all scenarios. A scenario scorecard was developed to assess the favorability of a project used to fill a gap. 5 scorecard criteria were developed to evaluate projects compared to each other as indicated on this slide. Scenario applicability assesses if that project will fill a gap across one or more scenarios. The more scenarios it addresses, the better. Similarly, but a little different, within the same scenario, a project that fills more gaps is more favorable. Life cycle costs are another important consideration. The total life cycle costs include construction, operation and maintenance, and other projected costs. Water quality impact considers impacts associated with development, as well as changing water and wastewater use. A project that provides higher protections to water quality ranks higher. Finally, a project with a shorter implementation time would be considered more favorable since the benefits of that project would be realized sooner. Few slides provide solution strategies for the 2040 full speed ahead scenario. Note that findings of the resources gaps were previously discussed and can be further explored using the dashboard planning tool. The dashboard facilitates scenario planning where gaps in other scenarios may also be filled with projects. Generally, the projects provide solutions for gaps beyond the 2040 full speed ahead scenario. Pre-planning level projects are provided as examples and possible solutions to fill gaps. Additional efforts are needed to define, plan, and implement a project as outlined in next steps. Further detail on these gaps is provided in tabular format on the next slide. Projects were categorized by type. Local, where a utility largely uses its own assets to fill gaps, or industrial users provide their own on-site solutions. Regional, where a utility collaborates with other utilities. And reuse, where a utility leverages reuse water to provide non-potable water to an industrial user to reduce potable water demand. This table provides detailed information on the projected resource gaps in the 2040 full speed ahead scenario in Perry County. The new Straitsville wastewater treatment plant does not cater to any industrial demands. It has only one municipal demand. This municipal demand is supplied with water from Burr Oak, which provides water to the majority of Perry County. Both New Lexington Reservoir and New Lexington Water Supply Reservoir are used for source water for the New Lexington Water Treatment Plant. Low surface water supplies are predicted in these two reservoirs, which could affect the New Lexington Water Treatment Plant. The new Straitsville wastewater treatment plant has a relatively small projected wastewater treatment plant gap of 0.02 million gallons per day. The timing and right sizing the expansion of the wastewater treatment plant should be aligned with the village's priorities. Due to the size of the gap, New Straitsville should monitor growth and consider smaller projects like an equalization tank or I&I reduction, which can be employed at lower costs. If population continues to grow in the village, a general option was developed to provide an additional 0.1 MGD of capacity as needed for future growth. The expansion of the existing New Straitsville wastewater treatment plant assumes construction of a completely new treatment facility with no use of existing facilities. The village may be able to combine the expansion with use of existing facilities to reduce infrastructure requirements. This option was then evaluated using the project scorecard. The New Lexington reservoirs were projected to be a resource gap by the study's model. The reservoirs are the source water for the New Lexington water treatment plant. The model predicted that during dry periods, reservoir remaining usable storage would be 0. This would strain the New Lexington water treatment plant's ability to supply water to the municipal demand. Regional connections, such as to the Burr Oak Regional Water District, could provide water supply in emergency conditions. This next section will present the evaluation conducted to determine areas of opportunity, which are defined as areas where there is assumed modeled surplus capacity. It should be noted that this section only identifies potential areas for opportunity. Project planning and utilization of surplus capacities will require further evaluation and discussions with local municipalities and stakeholders. First, water supply areas of opportunity will be discussed. Raw water supply sources in the county have opportunity for growth. There is surface water opportunity on Rush Creek. There is also usable raw water storage available at the Somerset Reservoir. There is no groundwater opportunity in the county. While the current aquifers are not over-allocated, the remaining supply should be preserved for existing users. Next, We looked at the areas of opportunity or surplus resources with regards to water and wastewater infrastructure. While there are few infrastructure gaps, the available water and wastewater capacities in Perry County are all less than 1 million gallons per day, which, while they are sufficient for their current demands, do not provide opportunity for growth. This next section will present the project findings relative to projected water quality across the planning horizon. While the Central Ohio Regional Water Study was primarily focused on water supply and treatment capacity, the models developed were also used to project potential impacts to water quality that may occur due to the changes in population, land use, infrastructure, and future temperature and precipitation changes. The goals for the water quality assessment were to characterize existing water quality conditions. The study identified watersheds with the highest existing water quality. Such pristine watersheds were considered to be the most sensitive to future development. Determine potential impacts. The study developed potential impact factors based on available data and the suite of possible future scenarios, including those evaluated for water supply and treatment. Watersheds were characterized as having higher or lower potential for impacts based on the identified impact factors. The scenarios use a range of future conditions. The intent is to illustrate where water quality impacts will likely occur. And finally, to provide recommendations and activities that could be completed by local agencies, utilities, and organizations to help offset, mitigate, and protect against water quality degradation. The graphic illustrates the approach to characterizing existing water quality and understanding the potential for future impact. Those watersheds with both high existing quality and high potential for future impacts should be considered as the highest priority for action. Watersheds throughout the region were characterized using the following 3 metrics. 1. Quality of aquatic habitat. This is a standardized metric for measuring the quality of aquatic habitat at a specific location within a stream. The average QHEI score in a watershed was calculated to determine the overall aquatic habitat score. 2. Targeted water quality standards. The aquatic life use designation, as well as anti-degradation tiers, provide a listing of streams that are targeted to remain high quality. These are assigned by stream reach for each HUC 12 watershed. The reach categorizations for anti-degradation and aquatic use designations were evaluated to determine an overall categorization at the watershed level. And 3. Stream biological health. The Ohio EPA has performed modeling to estimate the potential biological health of headwater streams based on land use factors and a desktop analysis. This modeling generated an estimate for all of the headwater streams in each watershed. A summary categorization of the results was applied to each watershed based on all of the stream reaches within its boundary. Given the factors above, an overall water quality category was applied to each HUC 12 watershed, ranging from poor to excellent. For Perry County, the majority of the watersheds scored as good or excellent, with a few small exceptions. 4 factors were used to determine the potential for future impacts to water quality. The first was land use. The population and land use projections provided by MORPC were used to estimate the overall change in the percent impervious of the watershed as estimated to occur by 2030, 2040, and 2050. Literature data has shown that increased impervious area in a watershed is typically correlated with decreasing water quality. As impervious area increases, the overall stream water quality tends to decrease. Second is hydromodification. When streams see higher flows and/or more frequently occurring storm events, stream banks may experience increased erosion. With these flow changes, streams may become incised and disconnected from floodplains, resulting in a decrease in water quality and increase in suspended solids. Next, increased occurrence of low flows. During dry weather conditions, healthy streams may typically maintain base flows to support aquatic life. If the low flow periods are extended or flows are projected to be lower under future conditions, it could have a negative impact on water quality due to loss of aquatic habitat and could therefore lead to more restrictive permitting requirements. Finally, temperature and precipitation. Changes in temperature and precipitation were considered in multiple scenarios. The stream model was again used to evaluate the impact of temperature and precipitation conditions during low flows. In some watersheds, the impact of temperature and precipitation on stream flows was found to be more significant due to lower flows during dry conditions that were not able to be offset through either wastewater treatment plant effluent or increased runoff. Impacts on water quality were evaluated based on projected changes both to population and land cover. The population and land use projections were provided by the Mid-Ohio Regional Planning Commission, or MORPC. The data was used to estimate the overall change in percent impervious within each watershed. The colors reflect the absolute percent increase in impervious area. Thus, a 5% increase in impervious area would indicate that the total percent imperviousness in the watershed would increase from 10 to 15%, for example. Literature data shows a strong correlation between stream conditions and the percent impervious for a watershed. As the percent impervious increases, water quality tends to decrease, particularly in areas without appropriate setbacks, mitigation, or stormwater controls. Hydromodification impacts. When streams see higher flows and/or more frequently occurring storm events, stream banks may experience increased erosion. With these flow changes, streams may become incised and disconnected from floodplains, resulting in a decrease in water quality and increase in suspended solids. A stream model was developed for the entire 15-county service area to stimulate stream flow from runoff as well as from wastewater treatment plant infrastructure. Future scenarios were developed that examined the impact of changes in population, land use, and temperature and precipitation on projected flows. 40 years of simulated stream flow were analyzed to determine the impact of different future scenarios on projected flows. Flows from the model were used to determine which watersheds may have a higher potential for channel modifications due to changes in flows. Watersheds in dark blue have higher potential for future hydromodification impacts based on the regional watershed model. For watersheds with a downstream modeled link, any of the watersheds that saw a 10% or higher increase in projected flows during frequently occurring storm events were designated as having a higher potential for hydromodification to occur. The watersheds with a lower potential may still experience hydromodification in isolated instances, but changes are not projected to be as significant given the range of forecasted scenarios. Increased occurrence of low flows. During dry weather conditions, healthy streams may typically maintain base flows to support aquatic life. If these low flow periods are extended or flows are projected to be even lower, it may have a negative impact on water quality and lead to more restrictive permitting requirements. The stream model was used to simulate stream flow from runoff as well as from wastewater treatment plant infrastructure. Future scenarios were developed that examined the impact of changes in population, land use, and temperature and precipitation on projected flows. 40 years of simulated stream flow was analyzed to determine the impact of different scenarios on projected flows. Flows from the model were examined, and an evaluation of flows during the driest periods was conducted to determine which watersheds may have a higher potential for water quality impacts due to decreased base flows during drier periods. Watersheds in dark purple have higher potential for future water quality impacts and more restrictive permitting requirements related to increased occurrence of low flows. For watersheds with a downstream modeled link, any of the watersheds that saw a 10% or greater decrease in projected flows during low flows were designated as having a higher potential for water quality impacts. The watersheds with a lower potential for low flow impacts may still experience impacts due to drier conditions and isolated instances, but changes are not projected to be as significant or as widespread given the modeled results from the range of forecasted scenarios. As noted, these areas are not indicative of any potential water supply or availability concerns, but instead indicate areas where low flows could impact habitat and permitting requirements. Temperature and precipitation. Changes in temperature and precipitation were considered in multiple scenarios. The stream model was again used to evaluate the impact of temperature and precipitation conditions during low flows. In some watersheds, the impact of the changing temperature and precipitation on stream flows was found to be more significant due to lower flows during dry conditions, especially areas that were not able to offset low flow through either wastewater treatment plant effluent or increased runoff. The model used 40 years of simulated stream flow to determine the impact of different scenarios on projected flows during drier periods. In some watersheds, the impact of temperature and precipitation on stream flows was found to be more significant due to lower flows during dry conditions that were not able to be offset through either wastewater treatment plant effluent or increased runoff. Watersheds in dark blue have higher potential for future low flow impacts due to temperature and precipitation change. A high impact, hot, dry, temperature and precipitation scenario was compared against a medium impact temperature and precipitation scenario. For the high impact scenario, if the base flows were lower than those in the medium impact scenario, then the watershed was flagged as having a higher potential for water quality impacts due to temperature and precipitation conditions. In some cases, high temperature and precipitation impacts were found to be slightly offset through increased wastewater treatment plant effluent and additional runoff from impervious areas. Overall, these areas flagged as high potential for temperature and precipitation impacts are those areas that may be slightly more vulnerable to temperature and precipitation impacts. All of the watersheds experienced some impacts and flows due to changes in temperature and precipitation. With potential water quality impacts identified, considering water quality protection is the next step. Water quality protection is a critical part of any water resource plan. It is important to understand that streams are constantly changing due to a number of factors, including vegetative communities, adjacent land uses, and changing temperature and precipitation. The magnitude of change over the next few decades will vary across the region and is subject to several variables. Current development plans indicate that development pressure is being increased in areas that are rapidly developed. Proper protections should be in place prior to development and significant land use changes in order to protect local water quality while supporting economic development. Proactive watershed engagement may reduce or eliminate negative impacts of development on water quality. 4 categories of solutions should be considered, including policy, partnerships, data, and funding that could be used to help offset or mitigate any potential future water quality impacts. Based on the findings of this study, there are some key locations that would benefit from prioritized protections. While all protective measures should be initiated across the region, immediate focus should be directed to protecting the high water quality watersheds with a high potential for future impacts. Local ordinances should be revisited on a routine basis to ensure they adequately address the changes the region is facing. In general, policies should be revisited on a routine basis to ensure they align with one another, are well supported with responsibilities delegated appropriately, and adequately protect natural resources. Riparian setbacks protect riparian buffers that reduce runoff and pollutants. Floodplain requirements ensure adequate space is available during storm events for systems to overflow their banks without flooding infrastructure. Stormwater management plans lay out best management practices for reducing stormwater runoff. Zoning and planning codes restrict development to certain areas, and in doing so can be used to protect valuable resources. Tree codes can encourage strategic planting of native and temperature and precipitation resilient trees, which compose riparian buffers and promote stormwater infiltration rather than runoff. Fee rates established for the Planning Commission and the Soil and Water Conservation District should be reviewed to ensure they adequately support proper review. These ordinances may be implemented at various levels, in which case a designated authority should be tasked with inventorying where the policies are and are not in effect, and to encourage collaborative efforts. The county should push to have 9-element non-point source implementation strategies, or NPSIS plans, in place as early as possible. NPSIS plans are defined at the HUC 12 watershed level. There are 27 HUC 12 watersheds completely or partially located in Perry County, of which 2 have an Ohio EPA approved NPSIS plan in place. Depending on when TMDL plans are estimated to be complete, the county may need to consider fast-tracking NPSIS plans in order to be eligible for 319 funding and to help define and prioritize projects. The NPSIS is a living strategic planning document that summarizes causes and sources of impairment, establishes critical areas, identifies quantifiable objectives to address causes and sources of impairment, and describes projects designed to meet those objectives. The NPSIS is designed to evolve as projects come and go, and will need to be reevaluated periodically, similar to the regulations mentioned above. MS4 compliance. NPDES permits are routinely updated. Every 10 years, urban areas are redefined by the Ohio EPA based on census data. The next census will be in 2030. Communities need to need to be prepared if they are close to reaching that threshold. Consider eventual need for separating permit administrative duties as communities approach urban area definition. Consider adopting additional regulations for areas experiencing rapid development that are not within a defined urban area. Ensure plans and resources are in place to support adequate preparation and review of an increased number of PTI and NOI applications. Ensure resources are in place to support increased number of SWIP reviews and construction site inspection. Educate communities on grant funding and other mechanisms available to support compliance with local water quality initiatives. MS4 communities can leverage a NPSIS plan to meet permit requirements by identifying watershed-specific strategies and projects that improve water quality. By integrating data collection efforts from NPSIS plans into MS4 compliance activities, municipalities can improve regulatory efficiency, strengthen funding opportunities, and enhance water quality improvements. 16 HUC 12 watersheds impacted by acid mine drainage. Currently, 15 have an Ohio EPA endorsed AMDAT plan, which is a specialized plan focused on mine drainage. And NPSIS addresses various types of non-point source pollution. A NPSIS plan is required for Section 913 funding, while an AMDAT plan is developed as part of mine reclamation efforts or as a supporting document for a watershed restoration. An AMDAT can be incorporated into a NPSIS plan. Strengthen partnerships between municipalities, watershed organizations, and other local governmental agencies. Communities don't need to work alone. Planning efforts are typically developed with input from state and local agencies, watershed groups and nonprofits, soil and water conservation districts, and universities and research institutions. By coordinating efforts with these stakeholders, communities can collaborate, get together and coordinate current issues and upcoming plans, meet regularly to discuss trends, projects, and upcoming plans. This can be outlined in stormwater master plans and can be expanded upon to involve additional stakeholders to discuss overall watershed action items. Invite guest speakers to learn about new opportunities. Representatives from existing partnerships or outside agencies can share success stories, lessons learned, and upcoming opportunities for projects and funding. Collaborate data collection and permit review responsibilities. Ensure responsibilities are delegated appropriately and that all partners have the resources they need to carry out said responsibilities. Link data between agencies through GIS. Pull the data collected and create a GIS database that is linked. This allows for partners to readily use data that is already available. Make data accessible via a GIS viewer with a user-friendly interface. Make information available for use and for partners to recognize where gaps in data may exist. This also allows partners to build on work that has already been completed. More on this in the next slide. Increase community engagement and participation with existing watershed partners to create a network of support for managing water quality challenges. Support programs that provide training on data collection for monitoring water quality indicators. Citizen scientists can help collect valuable data and observations This helps engage and inform the community. Facilitate educational opportunities with the public through outreach and training. Utilize NPSIS plans to identify partners and outreach resources. Host a platform to collect public observations and concerns. This is useful for monitoring spatial changes over time, as well as identifying key areas of concern for community members. Monitor water quality. Bolster local data collection efforts through training and certification programs. Monitor development impacts. Implement long-term monitoring programs to assess the cumulative impacts of population growth and development on water resources. Educating communities about the importance of water conservation and pollution prevention can encourage responsible behavior, and involving communities in data collection is a great way to encourage grassroots efforts to take place. Use monitoring data to inform revisions to watershed management plans and policies, ensuring they reflect current and future challenges posed by population growth. Digitize records. Encourage the use of GIS viewers to store available data collected by various governmental and public entities. Digitize existing record drawings and georeference new development records as they are constructed. Ensure data is collected equitably across the county, focusing on watersheds with high quality features and those experiencing ongoing issues or areas adjacent to and notably downstream of new development. Public reporting. Collect observations of flooding, erosion, and general water quality and store records digitally for analysis and reference. This will help identify areas of concern that are being felt by the community. Share monitoring results with the public and stakeholders to increase transparency and accountability. The figure shown is a screenshot of some of the layers the Northeast Ohio Regional Sewer District has available to the public on their GIS viewer. Red dots show public reported flooding. Storm sewers are depicted and attributes from records and inspections are stored. Attributes including pipe size, material, depth, and age are readily available and spatially referenced. Inspection data can be tagged to assets for tracking purposes. Department of Health IDDE sampling locations and results are also available. USGS stream gauges are linked, as well as ODOT bridge inspection data. Planning studies are identified that include reports and recommendations for the problem areas where available. Water quality protection mechanisms. Prioritize infrastructure upgrades. Secure funding for critical infrastructure such as stormwater management systems, wastewater treatment plant upgrades, and failing septic system replacements to support growing populations. Focus on areas identified as current or near-term gaps. Consider future scenarios to inform planning decisions. Assess regional optimization of services as early as possible. Incentivize sustainable practices. Establish funding programs to encourage developers to adopt green infrastructure and other low-impact development techniques that minimize the environmental impact of new construction. Stormwater best management practices include bioretention, pervious pavement, and extended detention. Encourage redevelopment over new development where possible. Proactively identify areas that are suitable for redevelopment. Leverage grant programs. Clean Ohio Green Space funding is available for preserving green space or riparian areas through Ohio. This fund may be used for property acquisition. Ohio EPA Water Resource Restoration Sponsor Program. Nonprofit organizations, parks, and municipalities may apply for funding to protect or restore high-quality water resources as an implementer. Competitive annual process will connect recipients with a sponsor. Interest from the sponsor's WPCLF loan ideally pays for the implementer projects. Muskingum Watershed Conservancy District offers a Partners in Watershed Management Project Assistance Program and NPSIS Development Grant Funding. This program provides assistance to local communities, agencies, and groups involved in projects and programs that support the conservation and flood control aspects of the mission of the Muskingum Watershed Conservation District. There are 4 funding streams currently: Stream Gauging Program, FEMA Hazard Mitigation Assistance, Debris Removal Program, and Acid Mine Drainage. Foundation for Appalachian Ohio offers multiple grants, 3 of which are applicable: community grants, research grants, and innovation grants. This is made possible by grant monies provided by the Muskingum Watershed Conservancy District due to the proximity within the Muskingum watershed. Section 319 grant funding is available, and the Ohio Department of Natural Resources Division of Mineral Resources Management Acid Mine Drainage Set-Aside Program. Assistance can be provided in the form of subsurface drilling, development of watershed monitoring plans, laboratory analysis of water samples, matching funding for water monitoring, hydrology and engineering technical assistance, construction contract administration, and construction oversight. Once watershed restoration plans are developed for a hydrologic unit or a sub-watershed within a hydrologic unit, the Division of Mineral Resources Management may also provide matching funding for the purpose of construction of an abatement project. Individual projects are eligible to receive matching funds through AMDAT if such projects are within an approved hydrologic unit, and the project has been demonstrated to be a priority component of a watershed restoration plan. H2 Ohio provides funding through H2 Ohio Rivers and H2 Ohio Wetlands. The Rivers program has several grant funding opportunities. Those that are applicable are listed, as well as the coordinating state agency. Agricultural Incentive Program. In 2024, Governor DeWine announced a statewide expansion of H2 Ohio producer initiatives, making the initiative available for the first time to producers who farm outside of the western Lake Erie Basin. For the first round of statewide enrollment, ODA offered enough funding and resources to enroll a new 500,000 acres outside of the western Lake Erie Basin. More than 525 producers in 51 additional counties enrolled in 2024. The program incentivizes farmers to implement science-based, proven best management practices to prevent nutrient runoff and improve water quality. ODA works closely with county soil water conservation districts to administer participant contracts, provide technical assistance, and support producers. The U.S. Department of Agriculture and the state of Ohio are partners in implementing a voluntary Conservation Reserve Enhancement Program, CREP program, to enroll up to 67,000 acres of agricultural land in the Lake Erie watershed and to enroll up to 70,000 acres of agricultural land in the Scioto River watersheds within the state of Ohio. Participants receive financial incentives from the USDA to voluntarily enroll environmentally sensitive cropland or pasture land in contracts for a period of 15 years. In return for annual rental payments that average approximately $150 per acre, participants may convert the land to native grasses, trees, and other conservation vegetation. Chloride Reduction Grant Program. A new partnership between the Ohio EPA and the Ohio Department of Transportation is focused on reducing salt pollution in Ohio's waterways. The H2 Ohio Chloride Reduction Grant Program now offers grants to communities to help them improve road salt storage and handling to reduce salt runoff into Ohio streams, rivers, lakes, and groundwater. Equipment grants. Ohio EPA awarded more than 250 communities across the state a total of $1 million in grants for equipment needed to maintain their public drinking water infrastructure. The grants cover distribution system equipment such as mobile leak detectors, line locators, valve exercisers, flow meters, hydrant condition assessors, pressure monitors, and training to use the equipment. In 2024, a second round of grants were awarded to over 250 communities for a total of $2.2 million. Equipment obtained under the grant must be used to exercise distribution system valves, perform leak detection on the distribution system, and for meter accuracy testing. Healthy Rivers Livery Grant Program. The program will support livery owners in removing trash from rivers and addressing long-standing cleanup needs. The grant will support up to $10,000 in costs to clean up Ohio's rivers and streams. Dam removals. The H2 Ohio Rivers program is also focused on removing low-head dams across the state that have outlived their intended use and are harming water quality through oxygen depletion, trapped sediment, and interrupted fish migration. Water infrastructure funding. Ohio EPA, through H2 Ohio funding, has awarded grants for a variety of water infrastructure improvements, including home sewage treatment system replacement, collection and conveyance system improvements, and treatment works upgrades. The H2 Ohio Statewide Wetland Grant Program is a reimbursement grant program that provides up to 100% project funding for high-quality natural infrastructure projects focused on nutrient reduction and water quality improvement across the state of Ohio. Applications for grant funding for projects outside of the Western Lake Erie Basin are open annually. Types of eligible H2 Ohio wetland or natural infrastructure projects include wetland creation, hydrologic restoration of wetlands on hydric soils, hydrologic enhancement of existing wetlands, floodplains and repairing corridors, stream conservation channel design and floodplain restoration, restoration of forested riparian buffers, acid mine drainage abatement projects, dam removal and associated restoration, property acquisition if associated with water quality restoration project, and stormwater retention or green infrastructure projects. In summary, the Central Ohio Regional Water Study included an evaluation of projected residential and industrial growth, the associated increased water demand, available water resources and water-related infrastructure, including water and wastewater treatment plants. The study evaluated the adequacy of existing resources and infrastructure to meet projected increases in demand over a 25-year planning horizon. The findings for Perry County can be summarized as follows. Perry County is projected to experience residential growth in the near future. This growth has the potential to put stress on available water supply and related infrastructure. Water resource and infrastructure capacity was compared to projected water and wastewater demand. Future projects were identified to alleviate or offset projected gaps. Projects identified as part of this project have been designated as local, regional, or reuse focused to give a range of potential future investments. In addition, areas of opportunity have also been identified, which could lead to regional partnerships and a sharing of resources. As growth occurs through the county, plans and pathways for protecting local streams and encouraging sustainable development practices can be leveraged. If you have comments or questions regarding this presentation or the Central Ohio Regional Water Study dashboard, please refer to the website. Thank you.